After a brief introduction on band theory of solids, today we are going to start the first concept of this band theory of solids. And actually, we will discuss a very important theorem which is called Bloch theorem. Actually, you have seen in my introductory lecture on band theory that according to band model, the band model is actually based on one electron approximation. It means we discuss the motion of only one electron inside the crystal, and we follow the quantum mechanical approach. And you have also learnt that according to band model, the potential inside the crystal is created by the ion cores, although the contribution of the other electrons is also in the creation of potential, but that is ignored. Okay, that is not very significant. Okay, so the basic or the main source of potential inside the crystal is the ion cores. Okay, in free electron theory, you have seen that the potential inside the crystal is assumed to be constant, but in contradiction of this, in band model, we have assumed that the potential inside a crystal is not constant, but it varies with the position of electron in periodic manner. And the period of the variation of the potential is equal to the lattice constant. Okay. So definitely, first of all, a question arises that how we can solve the Schrodinger equation set up for a single electron if it moves in a periodic potential. Actually, this Bloch theorem provides the technique how to solve what will be the solution of a Schrodinger equation when the electron moves in a periodic potential. And you will see that by this concept, first of all, the idea of the field, idea of the allowed energy bands, you can say, and the forbidden energy gap was found by this Bloch theorem. Okay. So first of all, we will learn about what is this Bloch theorem, how we can prove it, and then you will see that what is the application of this Bloch theorem in inventing the idea of allowed energy band and the forbidden energy band. Okay. I hope all of you are very acquainted of the solution of time-independent Schrodinger equation for a particle moving in a constant potential or zero potential. As you have learned in particle in a box, also in the course provided by me in quantum mechanics, and also in this free electron theory of metals, that when a single electron moves in a constant potential V naught, when you say constant potential V naught, this V naught is not a function of position of the electron, and it is also not a function of time. Okay, so time does not involve here. In that condition, in one-dimensional case, Schrodinger equation is written like this. You know it: d2 psi by dx square plus 2m over h bar square E minus V naught psi equal to 0. You know, this E is actually the total energy of the electron and V naught is its potential energy. So E minus V naught simply represents the kinetic energy of the electron. And this kinetic energy, you know, is classically given as P square over 2m, where P is the momentum of the electron. But in quantum mechanics, you have learned that this P is equal to h bar times k. Okay. Here k is the wave vector. And so you can write that this E minus V naught, which represents the kinetic energy of the electron, is given by h bar square k square over 2m. Okay. And what is the solution of this Schrodinger equation when potential is constant? You know very well, you have studied it earlier, that the well-known solution of this time-independent Schrodinger equation when electron moves in a constant potential are simply plane waves. Okay, so the solution of this equation 1, you know, is given as psi of x equal to e to the power plus minus ikx. Actually, when we normalize the function, we also write it as psi equal to a times e to the power plus minus ikx, where a is a constant which is known as normalization constant. But the nature of the wave function does not depend on this constant. It depends on e to the power plus minus ikx, which is called actually plane wave. Okay, so in nutshell, you can say when an electron moves in a constant potential field, then the Schrodinger equation for that equation has a plane wave solution. Okay, but here our problem is different, because we are now going to see the motion of a single electron, because band theory is based on one electron approximation. So we will talk about only one electron. Okay, and that electron, you should assume, is moving in a periodically varying potential. So if the one electron is moving in a periodically varying potential whose period is actually equal to period of the lattice, or period of the which is equal to lattice constant, then what will be the solution of that very Schrodinger equation? Actually, Bloch theorem answers this question. Okay, you can see I have assumed here that there is a linear lattice, and all these small spheres which I have shown in this figure actually represent the lattice points. Okay, and ions are actually attached with these lattice points. Okay, and the lattice constant I have assumed here is A. It means in this case the periodicity of the lattice is A, and so the periodicity of the potential V of x will be also A. And if you say that V of x has a period equal to A, what does it mean? It means V of x is equal to V of x plus A, it is equal to V of x plus 2A, it is equal to V of x minus A, and so on. Okay, so you can say that since our potential is periodically varying and its period is A, so we can write V of x equal to V of x plus A. Now, to solve the problem, to know the behavior of the solid, we will have to set up Schrodinger equation in one dimension for the electron moving under this periodically varying potential. And Schrodinger equation will be at each. You can see this will be d2 psi by dx square plus 2m over h bar square times E minus V of x psi is equal to 0. Okay, you can mark what is the difference between this Schrodinger equation which I have written in equation 1 and the Schrodinger equation written in this equation 3. Both have been written for a single electron moving in a potential, but the difference is in the nature of potential. Earlier in this equation 1, we have assumed that our electron is moving in a constant potential field, but here this V of x is not a constant potential field, but it varies with position x in periodic manner. And you can say that this V of x and V of x plus A, V of x plus 2A, all are same. Okay, so definitely the Schrodinger equation should have not the plane wave solution in this case, because the nature of potential under which electron is performing its motion is different. In fact, in 1928, Felix Bloch gave the technique of solving this Schrodinger equation. And according to Bloch, the solution of this Schrodinger equation defined in equation 3, where potential function is a periodically varying potential, that is not simply the plane waves, but these are plane waves modulated by a function uk of x, and this function uk of x have same periodicity as that of the lattice. Okay, so according to Bloch theorem, the solutions of this Schrodinger equation defined in equation 3 will be given by the product of the plane waves, that is e to the power plus minus ikx, and this function uk of x. And this function uk of x is also a periodically varying potential having the period equal to the period of the potential, and that is equal to lattice constant. So you can write the solution of this equation 3 in this manner. This is given as psi of x equal to e to the power plus minus ikx times uk of x. Okay, and as I have told you, this uk of x is also equal to uk of x plus a. Okay, actually this statement is known as Bloch theorem. Okay, and in the theory of differential equation, such an equation is also known as Bloch's theorem. Okay, so you can say Bloch theorem as Bloch's theorem in accordance with the theory of differential equation. Okay, and the function defined in this equation 4, these are actually called Bloch functions. So you can say that Bloch functions are simply the solutions of the Schrodinger equation for a single electron moving in a periodically varying field, periodically varying potential. Okay. Now, till now we have assumed the motion of a single electron in a one-dimensional lattice. But you know, practically lattice is three-dimensional. So if your aim is to write the three-dimensional equivalent of the Bloch theorem, then you have to set up Schrodinger equation for a single electron moving in a three-dimensional lattice. Okay, and in that lattice too, the potential will vary periodically. So you can see I have written here the time independent Schrodinger equation in case of a 3D lattice for a single electron, and this is given as minus h bar square over 2m del square plus v of r psi of r equal to e times psi of r. Okay, this is Schrodinger equation in 3 dimensions, and here this potential v of r is periodically varying potential, and in this case the solution of this equation in accordance with Bloch theorem, you can write in this manner: psi k of r equal to plane wave e to the power plus minus ik dot r times uk of r. So again you can see the solution of a Schrodinger equation for a single electron moving in a periodically varying potential is simply the plane waves modulated by a function uk of r, and this function uk of r is also a periodic function having the same period as that of the potential. Okay, and that is equal to simply the lattice constant. Okay, so this is three-dimensional equivalent of this equation 4. Okay, this is your Bloch theorem. I hope you have clearly understand what is this Bloch theorem. Bloch theorem is nothing. This gives simply the solution of the Schrodinger equation set up for a single electron moving in a periodically varying potential. Okay, And as in case of crystal, the potential varies inside the crystal in periodic manner. So whenever we will discuss the uh, quantum mechanical theory of solid, we will have to set up Schrodinger equation for a single electron, and the solution of that Schrodinger equation we will write with the help of this Bloch theorem. Okay, so this is your Bloch theorem. Now first of all we will see its proof, how we can prove the Bloch theorem. Okay, actually when you say that you have to know about the proof of this Bloch theorem, what does it mean? You can see that this psi of x which is equal to e to the power plus minus ikx times uk of x. This is actually the solution of one-dimensional Schrodinger equation for a single electron moving in a periodically varying potential. Okay. But you have also seen that this uk of x also varies in periodic manner, and so uk of x is equal to uk of x plus a. So this solution will be equivalently correct when we will replace x by x plus a. So let us replace x by x plus a in this equation 4. And you can see in this condition we can write psi of x plus a is equal to e to the power plus minus ik x plus a. Here x has been replaced by x plus a. And at the place of uk of x, now we will write uk of x plus a. Okay. But you have seen that this uk of x is simply equal to ukx, because this is a periodically varying function. And this e to the power plus minus ik times x plus a, this can be written as e to the power plus minus ika times e to the power plus minus ikx. But you can see the product of this plane wave e to the power plus minus ikx and uk of x, what is this? This is simply psi of x. You have learnt. This psi of x is what? This is e to the power plus minus ikx times uk of x. You have seen. So instead of this e to the power plus minus ikx times uk of x, you can write psi of x. So psi of x plus a is simply equal to e to the power plus minus ika times q psi of x. Here you can see this e to the power plus minus ik is a constant factor. And if you assume that this e to the power plus minus ika is equal to q, then you can write psi of x plus a is equal to q times psi of x. Okay. So actually if you have to find the solution of this the proof of this Bloch theorem, you will have to prove it. And you will see later on this q will have actually two values. And considering its values, we will discuss how the band model arises from this Bloch theorem. Okay. Now let us see. This equation 3, which is actually Schrodinger equation in one dimension, this is simply an ordinary differential equation of second order. And you know from the theory of differential equation that a second order ordinary differential equation has two independent solutions. If the order is 2, the equation will have two independent solutions. Okay. And the linear combination of those two independent solutions will be also the solution of that very differential equation. But although we also say that that is the most general solution, which is obtained from the linear combination of the independent solutions of the differential equation. So since Schrodinger equation is an ordinary differential equation of second order with constant coefficient, so it will have definitely two real and independent solutions. And let us assume that those two real and independent solutions of Schrodinger equation defined in that equation 3 are f of x and g of x. Okay? And you also know from the theory of differential equation that the solution of a differential equation satisfies the equation. Okay? So if this f of x and g of x will be substituted at the place of psi, the equation will get satisfied. Okay? And again I have told you, if f of x and g of x are the two independent solutions of Schrodinger equation defined in equation 3, then a linear combination of f of x and g of x will be the most general solution of this equation. So you can write the most general solution of that very Schrodinger equation in this manner. This is psi of x equal to a times f of x plus b times g of x. When you multiply f of x and g of x by arbitrary constant and you add it, you get the linear combination of these two solutions, and that gives actually the most general solution. So you can say that this equation 9 is the most general solution of our Schrodinger equation defined in equation 3. Okay? And as I have told you, actually a and b are actually the arbitrary constant. In fact, these are integration constant, because you know, when actually a second order differential equation will be solved, what we will have to do? We must integrate that equation 2 times. And since integration will be done for getting the solution 2 times, so there will be 2 integration constant. And actually a and b are those 2 integration constants. Okay? Now one thing you have seen that here our electron is moving in a periodically varying potential whose period is a. So v of x is equal to v of x plus a. Okay? Actually the nature of this potential also governs the nature of the solution. Since potential v of x is equal to v of x plus a, so you can also say that f of x plus a and g of x plus a will be also the solution of that very Schrodinger equation, in addition to the solutions f of x and g of x. Okay? However, that equation 3 cannot have more than 2 independent solutions, because you know that is a equation of second order. So this function f of x plus a and g of x plus a are not independent solutions. Mark it. F of x and g of x, these are independent solutions. F of x is completely independent of g of x, and g of x is completely independent of f of x. But if you are telling now that this f of x plus a and g of x plus a are also the solution of Schrodinger equation, can these f of x plus a and g of x plus a be independent solution? Answer is no, because that Schrodinger equation can have only 2 independent solutions, and you have assumed already that f of x and g of x are the 2 independent solutions. So f of x plus a and g of x plus a are not independent solutions, but these are dependent solutions. When you say dependent solution, what does it mean? It means f of x plus a and g of x plus a ultimately depends on f of x and g of x. And so we can express these solutions f of x plus a and g of x plus a as a linear combinations of the 2 independent solutions f of x and g of x. So you can write that f of x plus a is equal to alpha 1 times f of x plus alpha 2 times g of x. So this is a linear combination of f of x and g of x, which gives you f of x plus a. And in the similar manner, you can also say that this dependent solution g of x plus a can also be expressed as the linear combination of f of x and g of x. So g of x plus a can be written as beta 1 f of x plus beta 2 g of x. Okay. In fact, here these four constants, alpha 1, alpha 2, alpha beta 1, beta 2, all these four constants are real functions of energy E. Okay. It means alpha 1, alpha 2, beta 1, beta 2, these depend on energy E. Okay. And now, as we have assumed that f of x plus a and g of x plus a are also the solution of Schrodinger equation, so you can write another general solution of this Schrodinger equation in this manner as psi of x plus a is equal to a times f of x plus a plus b times g of x plus a. It is evident on the basis of this equation 9. You can simply say that if we replace x by x plus a in this equation 9, then we get psi of x plus a equal to this much. Okay. Now let us substitute the values of f of x plus a and g of x plus a from this equation 9 here. You can see f of x plus a is equal to this much. This is alpha 1 times f of x plus alpha 2 times g of x. And g of x plus a is equal to this much. This is beta 1 times f of x plus beta 2 times g of x. Okay. Now, we will simplify the RHS to some extent. You have to take f of x and g of x as a common factor. Okay. And so, after collecting the terms and taking f of x and g of x as common factor, you can see we get psi of x plus a is equal to this much. This is a alpha 1 plus b beta 1 times f of x plus a alpha 2 plus b beta 2 times g of x. Okay. Now let us choose a and b in a particular manner. We consider that this factor a alpha 1 plus b beta 1, which is the multiple, which is the coefficient of f of x, that is equal to qa. We consider it. Okay. And the coefficient of g of x, that is a alpha 2 plus b beta 2, we assume that it is equal to qb. We assume it. So now let us use this equation 11 in this above equation. Okay. And you can see when you will substitute it in this equation, what will be our result? You can easily see. You can see that this will be psi of x plus a is equal to what? Instead of this a alpha 1 plus b beta 1, we will write qa. So this will be qa times f of x. Okay. And plus, instead of a alpha 2 plus b beta 2, we will write qb. So this is qb times g of x. Okay. Now you can take q as a common factor, and the remaining terms are a times f of x plus b times g of x. Okay. But you know, this a times f of x plus b times g of x, here you can see this equation 9, this is actually equal to psi of x. So instead of it, you can write psi of x. So this is simply q psi of x. So I have written here, you can see directly that psi of x plus a is equal to q times psi of x. Okay. And you have seen that this is actually what the Bloch theorem says here. Earlier I have written it here in this case. Okay. Now this see here. See this equation 11. Actually, this is a linear equation in A and B, and you can rewrite equations in 11 in this manner. Let us bring the terms in RHS in LHS in equation 11, and then you will get that equation becomes alpha 1 minus q times A plus beta 1 B is equal to 0, and alpha 2 A plus beta 2 minus q times B equal to 0. And you can see these two equations are actually the simultaneous equation, and according to theory of determinant, you can say these constants A and B will have non-vanishing value, non-zero value. When the A and B will have non-zero value, according to theory of determinant, when the determinant of the coefficients of A and B will vanish, will be zero, only then A and B will have non-zero value. So for getting the non-zero value of A and B, you have to equate the determinant of the coefficients of A and B equal to 0. And so you can see, you can write the determinant of q alpha 1 q beta 1 alpha 2 beta 2 minus q is equal to 0. And you can solve this determinant. You know, for solving it, we will multiply these diagonal terms, and then you will get q square equal to q square minus alpha 1 plus beta 2 times q plus alpha 1 beta 2 minus alpha 2 beta 1 equal to 0. I have skipped some steps here. You can do the algebra. Okay. Now our purpose is to show this last term alpha 1 beta 2 minus alpha 2 beta 1, this will be equal to 1. I am giving you a suggestion. When this question is asked in your examination, okay, then you can directly write that it is found that this alpha 1 beta 2 minus alpha 2 beta 1 is equal to 1. You can write it directly, and for this you have to remember it. Okay. But here I have provided the proof of this very fact. But in examination there is no need to write this proof. Okay. You can directly write that this term is equal to 1. And so your answer will be then very concise in your examination. But here you have to learn. So let us see how we can prove that this term alpha 1 beta 2 minus alpha 2 beta 1 is equal to 1. Okay. Actually, starting from the Schrodinger equation, we can prove it. Okay. As you have learnt earlier that this f of x and g of x are the two real and independent solutions of Schrodinger equation defined in equation 3. And you also know the solution of any differential equation satisfies the same equation. So you can write Schrodinger equation writing f of x and g of x at the place of psi of x. So in one dimension now we can write the two Schrodinger equations. First one is d2f by dx square plus 2m over h bar square times e minus b of x f equal to 0. And the another will be d2g by dx square plus 2m over h bar square times e minus v of x g equal to 0. Okay. Now, as we have to prove some result, that is, we have to prove that alpha 1 beta 2 minus alpha 2 beta 1 is equal to 1. For this, we will have to adopt some mathematical steps, and you have to see this seriously, and by practice you can remember it. Now, see, equation 14 is in terms of the function f, and 15 is in terms of function g. So remember a trick. The equation which is in terms of function x, now we will multiply it by the function g. And the equation which is in terms of function g, we will now multiply it by f. Okay, and then we will subtract any one equation from another. Okay, here I have subtracted this equation 14 from 15 after multiplication by g and f respectively. Okay, so let us see. I have multiplied the second equation by f, so this is f times d2g by dx square plus 2m over h bar square e minus b of x times fg. Okay, and equation 14 will be multiplied by g and subtracted, so this will be minus g times d2f by dx square minus 2m over h bar square e minus b of x fg equal to 0. Now you can see these two terms will cancel out, both are same but sign is opposite. So the remaining terms are the first term and this third term. These are the remaining terms. So you can write that this f times g double dashed minus g times f double dashed is equal to 0. Here actually when you write f double dash, that means the second order derivative of f with respect to x, and g double dashed is the second order derivative of g with respect to x. Okay, and this f times g double dashed minus g times f double dashed equal to 0 can be written as d dx fg dashed minus gf dashed equal to 0. In fact, when you will simplify this LHS, you will get two extra terms, but those two extra terms will cancel out. So you can do the algebra yourself. Okay, and you will see that d dx operated on this g f g dashed minus g f dashed will be ultimately equal to this much, that is f g double dashed minus g f double dashed. Okay, but you know, if derivative of a function is 0, that is a constant. So you can see that here f g dashed minus g f dashed definitely will be a constant. Okay, and if you want to write this equation in determinant form, you can write this is determinant of fx gx f dashed x g dashed x, and that will be equal to constant. Okay, now let us see this equation here. Sorry, see this equation. These are the equations. You have to see which equation. You have to see equation 10. Okay, so let us see equation. What is our equation 10? See this equation. Okay, actually this these two equations in equation 10 can be written in determinant form. You can write it, or in matrix form. You can write it. So what will be these two equations when we will write it in determinant form? You can see we can write the determinant of fx plus a, gx plus a, f dashed x plus a, g dashed x plus a is equal to this much times this much. You can easily check it. Okay, but in accordance with equation 16, this determinant is constant. When you say that this determinant is constant, what does it mean? It means when x will be replaced by x plus a in each term, then again the determinant will have the same value. Okay, so in this, on this basis, you can say that the determinant of f of x plus a, g of x plus a, f dashed of x plus a, g dashed of x plus a will be simply equal to determinant of f of x, g of x, f dashed of x, g dashed of x. Okay, so this LHS is equal to the first factor in RHS. So what will be the second factor? Definitely the second factor will be 1. Only then these two will be equal. So on this basis you can say that the determinant alpha 1 beta 2 alpha 2 beta 1, that is simply equal to 1, and this is written as alpha 1 beta 2 minus alpha 2 beta 1 is equal to 0. So you can see in this way we have proved that this term alpha 1 beta 2 minus alpha 2 beta 1 equals 1. And this I have told you earlier that for your examination purpose there is no need to prove this result. You can directly say that this term is equal to 1 and skip all these steps in your answer in your examination. Okay, and so then you can directly write that equation 13 in this manner, that this is q square minus alpha 1 beta 2 times q plus 1 equal to 0. Actually this is the most important result here, because you will see that the solution of this equation will give the idea of the allowed energy band in solids and the forbidden energy bands. Okay, as you can see, equation A is a quadratic equation in Q. Equation A is a quadratic equation in Q, and you know quadratic equation has two roots. So this equation will also have two roots. When you say it has two roots, it means there will be two values of this Q. Okay, so and what will be those two values? Now you can see the two roots can be given like this. This is alpha 1. I hope you have an idea of the roots of a quadratic equation. You know ax square plus bx plus c equal to 0. Then x is equal to what? This is minus b plus minus root over b square minus 4ac and divided by 2a. And comparing this quadratic equation with your equation here, you can see a is equal to here 1, b is equal to minus alpha 1 plus beta 2, and c is equal to 1. C is equal to 1. Okay, so the roots of this quadratic equations are like this. Okay, you can see it. And taking the plus minus sign separately, we will have the two values of q. So the first root is q1 equal to this much. This is 1 over 2 alpha 1 plus beta 2 plus square root of alpha 1 plus beta 2 square minus 4. And the second root q2 is equal to 1 over 2 alpha 1 plus beta 2 minus square root of alpha 1 plus beta 2 whole square minus 4. So these are the two roots of this quadratic equation, or two values of q. You can see. Now we will consider actually two situations. In first case or first situation, we consider the energy ranges such that this discriminant, this alpha 1 plus beta 2 whole square is less than 4. We consider it. And when we will consider that this is less than 4, you can see the values of these two roots. Then actually the root over alpha 1 plus beta 2 square and minus 4, this will be something a square root of negative. And you know a square root of negative will be iota times something. Okay, so both of these two roots q1 and q2 will be complex, because the first term here alpha 1 plus beta 2 is real and second term will be imaginary. So q1 and q2 both will be complex. Okay, again you know in case of a quadratic equation like this, what is this C by A? C by A, C by A. See here, C is equal to 1 and A is also equal to 1. Okay. So, and C by A, this is actually equal to the 2 roots alpha into, sorry, alpha into, here alpha beta are the two values of x. So alpha into beta, you know, this is C by A. So here Q1 into Q2, this will be equal to what? C is 1 and A is also 1, so this will be equal to 1. So you can say that Q1 is equal to 1 over Q2. But you know Q2 is a complex quantity. So 1 over Q2 will be its conjugate. So you can say that Q1 and Q2 are complex conjugate of each other. Okay. So one thing we get here, that when we assume that energy has such a value, because you know the values of alpha 1 and beta 2 depends on energy E. So if energy of electron has such a value that this term alpha 1 plus beta 2 whole square is less than 4, then both roots of this quadratic equation are complex, and they are also complex conjugate of each other. Okay. So if both are complex conjugate of each other, you can easily write what will be these roots. So if you assume that this Q1 is equal to e to the power IKA, then Q2 will be the complex conjugate of this, and that will be e to the power minus IKA. Okay. And in this condition, you can write the solutions of Schrodinger equation in this manner, or you can write the function psi1 of x and psi2 of x for these two values of q and q2 in this manner. Psi1 of x plus a is equal to psi1 of x times e to the power ik, because you have seen earlier that psi of x plus a is equal to psi of x times q. You have seen earlier. So on this basis, we can write that psi1 of x plus a is equal to psi1 of x times e to the power ik. And similarly, psi2 of x plus a is equal to psi2 of x times e to the power minus ik. So in general, you can write psi of x plus a is equal to psi of x times e to the power plus minus ik. And so this is nothing, this is simply psi of x plus a equal to q times psi of x. And this is what? This is actually the Bloch theorem. We have seen that according to Bloch theorem, this psi of x plus a must be equal to q times psi of x. And here q has been obtained like e to the power plus minus ik. And you can see that these two functions, psi1 of x plus a, psi2 of x plus a, satisfies the all required conditions, criteria for a valid wave function. Okay. So the electron in the crystal will have such an energy, or electron can exist on the energy state for which this condition is satisfied. Okay. Actually, that energy range is the electron in that energy range is called in the allowed energy band. We will see later on this fact. But now let us see the another situation. In second case, we consider that the electron has such an energy that this factor alpha 1 plus beta 2 whole square is greater than 4. Let us see what will happen when we say that electron has such an energy for which alpha 1 plus beta 2 whole square is greater than 4. And you can see from this values of two roots, if alpha 1 plus beta 2 whole square is greater than 4, then this discriminant will be positive, and positive quantity have a square root which is real. So both Q1 and Q2 in this condition will be real, not complex. Are you getting the things or not? Definitely, this is a very easy concept. and you can see it. So in this condition you can say Q1 and Q2 both are real, and again since C by A is equal to Q1 into Q2 and that is equal to 1 here also, so Q1 into Q2 will be again 1, and that's why you can say that Q1 is equal to 1 over Q2, but Q2 is real. So you cannot say that this is complex conjugate of Q1 because Q1, Q2 are not complex. But you can say that Q1 is reciprocal of Q2, and similarly Q2 is reciprocal of Q1. So in this case both Q1 and Q2 are real and reciprocal of each other. So you have to now choose the value of Q1 and Q2 as real values and reciprocal of one another. So you can take, if Q1 is equal to e to the power mu a, where mu is a real number or a real constant, you can say it has a dimension of inverse of a. Okay. Then since Q2 is reciprocal of Q1, so Q2 will be equal to e to the power minus mu a. Okay. Here mu is real, as I have told you earlier. And so in this condition the solution of the Schrodinger equation will be written like this: psi 1 of x equal to e to the power mu x times u of x, and psi 2 of x equal to e to the power minus mu x times u of x. Okay. But let us check these two functions, psi 1 of x and psi 2 of x. Are these valid wave function? Answer will be no, because you know a function will be a valid wave function. For this it have to satisfy three criteria, and one of those criteria is the function must be bounded. When you say that function must be bounded, what does it mean? It means for any value of x from minus infinity to plus infinity, this function psi of x must be finite. If its value is finite for any value of x for the entire range of x between minus infinity to plus infinity, then the function is said to be bounded and it is a valid wave function. Okay. But these functions are mathematically alright, but you will check that these are not bounded function. How you can say it? Let us check. If x tends to infinity, what will be the value of e to the power mu x? This will be simply e to the power infinity, and e to the power infinity means infinity. So at x equal to infinity, this function psi 1 of x becomes undefined. But a valid wave function cannot be undefined for any value of x, even for x equal to infinity. And when you take x is tending towards minus infinity, then let us check what is e to the power minus mu x. This will be again e to the power infinity, and that will be infinity, that is undefined. So in this condition psi 2 of x becomes undefined. So these forms of the functions psi 1 and psi 2 refers that these are not bounded, so these are not valid wave function. So if these are not valid wave function of electron, what does it mean? It means electron inside a crystal cannot have an energy which satisfies these states. And so those states where electron will have such an energy, where the solution of Schrodinger equation will be like this, cannot exist. So those regions are forbidden region. Electron cannot remain there, and those regions are called forbidden regions or forbidden energy band. Okay. So you can see now that mathematically these solutions are valid, but these solutions are not acceptable as psi of x are is not bonded or finite everywhere. So what's the conclusion from these two cases? Now we will see. Although I have already told you, but let us now discuss it. You have seen that Q1 and Q2, which have been defined in equation 19 and 12, 22, depend on alpha and beta. You have seen. And alpha and beta depends on energy E. So you can say that Q1 is a function of energy E and Q2 is also a function of energy E. Okay. Now, in equation 9, the roots are allowed. Why these roots are called allowed roots? Because in this condition, the Schrodinger equation has a valid solution. Okay. But when you write the roots of the equation defined in equation 22, where the roots are real, then you see that the solution of Schrodinger equations are not valid because the functions are not bounded, they are not finite everywhere. Okay. That's why we simply say that the roots defined in equation 19 are the allowed roots, and these allowed roots are associated with allowed energy bands. Okay. But the roots defined in equation 22, where you have seen that the roots are real, that are associated, that are not allowed, that are disallowed actually. So those roots actually correspond, or they are associated with forbidden energy gap or band gap. It means no electron will be found there. So we can say, according to this Bloch theorem, the energy spectrum of an electron moving in a periodic potential consists of allowed band and the forbidden region. So you can say that if this is the allowed energy band, okay, this is called allowed energy band, allowed, and electron can remain here, and this is your again allowed energy band. Okay. But these two allowed energy bands will be separated by the forbidden energy gap. In forbidden energy gap, the electron will not exist, but here there will be electron present in these bands. Okay. So according to free electron theory, you have seen that there exist energy levels, discrete energy levels, according to free electron model. But according to this Bloch theorem, the energy levels are not present in the solid, but energy bands are present. The band in which electron can exist are called allowed band, and the band where electron cannot exist, such an energy of electron is not possible, that are called forbidden. And these allowed bands are not continuous. Actually, two successive allowed energy bands are separated by a forbidden energy gap. And this is the most important fact which we have obtained, or which we know from this Bloch theorem. So Bloch theorem is the basis of this band theory. Okay. Actually, we will see, using this theorem, we will discuss a very important band theory which is called KP model, Kronig-Penney model. Okay. So this was all about the band, all about the Bloch theorem. This is a very important concept and very useful to deal with the problem of band theory of solids. And I hope after this lecture, the concept of this Bloch theorem will be very clear to you. Okay. Thank you very much.